both those who are here in person and all those that are joining us online. So I am Shaun Edwards. I'll be leading this meeting. I'm the ROS-Industrial co-founder and a principal engineer at Southwest Research Institute. That's a picture of me, just so you know who's talking at you. Just a little bit of logistics, particularly for the online group. Everyone is muted, so only the presenters are able to talk. So any presenters that are remote, please mute yourselves when not speaking. That's basically just you, Mirko. Questions will be taken via the chat at each of the mini talks. So we have mini talks scheduled as part of this community meeting, and at the end of that talk, we'll take questions on specific topics. And also, all the chats are directed towards the presenter. That way, we see all the questions that are asked. And this event will be recorded, video and audio, and posted afterwards. We found that a lot of people actually watch this after the fact, particularly if they're in a part of the world where it's night at this point. So first, welcome, and I'd like to start off with some thank yous. First, to thank RoboUniverse for giving us a venue here from which to present and do the ROS-Industrial community meeting. Thank you to the ROS-Industrial Consortia for funding these kinds of efforts and allowing us to do this work. Thank you to Southwest Research Institute for supporting ROS-Industrial and allowing me and others to do this cool work. And finally, thank you to the community. Without the community and people out in the world helping us, this wouldn't be as big a project as it is. Here's our agenda. There's going to be some introductions from myself for the first 10 minutes, and then we'll move into kind of what I'm calling the mini talks. We have a lot of content from industry, which is different than previous community meetings, but I'm happy to say that that's a good change. So we're going to hear from Canonical, HTT, Intel, Blue Workforce, and then Fraunhofer IPA as well. I'm going to hold very tightly to this agenda, so any of our speakers, I will let you know when you're going over time. So just for some introduction, I thought I would show the ROS 8-year video. I know that not everybody actually sees these when they're posted online, particularly the people that come to the ROS-Industrial community meetings. So I'm going to show that and let that play through, and then maybe talk about some of the things that we see. So I'm going to share my desktop and show you the ROS video. So what you're going to see is just the amazing amount of robots that actually use ROS and run ROS. There's actually so many, it was really difficult to fit them all in this video. So there's actually a longer version that shows full screen shots of all these. But it's real impressive to see the variety of robots. Wheeled robots, drones, industrial robots, humanoid robots. But I think these source credits show a lot of all the different universities and commercial companies and research institutions that are using ROS. I think it's very impressive. So back to our slides. I would encourage everybody to go see the long form of that video. It's actually, to see what all the robots are doing is very, very impressive. It also takes like 8 minutes, 4 times as long, so you got to be patient. So that's the reason for the short form. So yeah, ROS is 8 years old. That makes ROS-Industrial about 4 years old. Why is that an important number? What does that mean? Mark Shuttleworth in his ROSCon talk talked about it takes 5 to 10 years to make an overnight success. And so I think we're seeing that with ROS, right? We're at 8 years and we're starting to see kind of acceptance by commercial companies. It's really starting to evolve into its own. Community meetings are evolving. It used to be that, we'd have these community meetings and be a bunch of researchers get up and talk about what they're doing with ROS. Now we have a bunch of commercial companies talking about what they're doing with ROS. Adoption is moving from within companies, from their R&D groups into production, right? So products are now based on ROS. Manufacturing R&D groups are now deploying systems in factories. We're seeing that. And I can tell you just in general, the conversation has changed from should we use ROS or ROS-Industrial to what is the best way to use ROS-Industrial? Or should we support ROS-Industrial to how do we support ROS-Industrial? And just those conversations are much easier to have now. So ROS has certainly kind of come into its own. So with that, I'm going to pass it on to our presenters, and we're going to see how these companies in particular are using ROS or see ROS as being of value. So the first presenter is Manik from Canonical, and he's going to talk about a new product from Canonical with regard to Ubuntu, and I'll let him go into that. Go on up. Get your slides up. Here we go.
Thanks, Shaun. Welcome, everybody, and good afternoon. Can you hear me in the back, by the way? Right on. So I wanted to quickly give you an overview of a new offering that Canonical is bringing in the IoT space, and we feel that it is very, very useful in the robotics space and something very unique as a platform to develop on for robotics. So with that said, where do we really see the future of robotics moving is towards software. The primary reason drones are starting to pick up more and more is because they have the capability to fly autonomously and thereby removing the human part of the equation, which is where the maximum cost in the equation lies. So we see more enablement in terms of voice interaction, video interaction, offering new capabilities by developing features and reusing the same physical hardware to essentially achieve whatever we want to achieve. Even in just a highlight, in the latest DARPA challenge, we had 80% of the robotics companies were using ROS on Ubuntu for their robots, and we have a good mind share in that community. We are bringing a lot of innovation in that market. So what is really Snappy? Snappy is a complete rethinking of what an operating system traditionally is supposed to do. And what it's offering right now is the capability to do transactional updates. It allows you to sandbox each application that is written in the user space. So each application can function at its own cadence, at its own speed, without having to worry about what else is installed on that machine. So if applications are bringing in their own dependencies, their own conflicts with each other, and they can function as if they are the only application installed on that machine, so in that case, on that robot or the drone. All this is achieved using standard Linux kernel primitives called AppArmor. And what this allows us to do is have a very clean separation between the kernel space, between the user space, and the application space, sort of creating a sandbox around each of them and offer guarantees around updates and rollbacks. So at any time, we can roll forward to a new software version on the system, or we can roll back to the previous known good state of the system in case the upgrade fails. We can do that automatically. So at any time, you don't have a broken device. And that's sort of the new way to think about an operating system and what an operating system can deliver and should deliver in this space. We are trying to create an amazing ecosystem for developers. We have developed a new tool called Snapcraft, which essentially allows you to create snaps, which is what each of these sandboxes are called, whether it be a kernel snap or operating system snap or an application snap itself. And we'll talk a little bit more about Snapcraft in just a few slides. So the OS itself is extremely tiny. The compressed image is 70 megs, and the decompressed image is about 500 megs. And we have taken all the bare minimal essential packages from the standard Ubuntu archive and made them available as a single cohesive operating system, which is essential for the functioning of the hardware. So anything you wish to add on top is really can be added with the help of frameworks, which allow you to extend where the operating system should be going. And then finally, of course, we allow you to create a white-labeled app store for any device that is running a Snappy operating system, and essentially be able to monetize it after the fact that the hardware has been sold to the end user, wherein third-party developers could develop applications for your device and could publicly sell and buy these applications to the community. So if we look at the difference between a traditional Ubuntu and a standard Ubuntu, where do we stand? Why did we come about with Snappy Ubuntu? The great thing about traditional Ubuntu is that we have a huge archive of debs. We have a lot of packages that have been tested thoroughly and easily available and consumable. But the bigger challenge is that in the traditional Ubuntu environment, or even any standard Linux distribution today, we have the concept of discretionary access control. What that means is any package can read or write wherever they like in the system, and essentially creating a system where two packages from two developers could be writing in the same file in etc, or could be changing shared libraries in the system, which are going to break another application from a third-party developer. And that's sort of the snowflake model that you see on the left. In the Snappy model, we have completely decoupled each and every part of the system. So we have a kernel snap, which is the hardware enablement. We have the OS snap, which is just the base operating system, the extremely tiny core to bring up the device. And then, of course, we have on the user space the application snaps itself, which allow the robot or the drone to do something meaningful in that instance. And then, of course, each of those snaps have their own writable space that is completely dedicated to that application itself, and only that application is allowed to write in that space, right? So if you think about a simple example of like, if you install Firefox today in standard Ubuntu, Firefox can read your private SSH key and do whatever Firefox wants with it. Firefox can in fact change the kernel on your operating system. But should Firefox really have access to your private SSH key, right? And that's sort of the new way of thinking that we are trying to bring in terms of an operating system which is completely contained, completely self-isolated. And each application can function as if that application is the only application installed on the device without having to worry about somebody else bringing in other dependencies that conflict with its own or changing configuration files in the system that affects its own configuration. So what does the Snappy model look like? So at the bottom we have the kernel and the hardware capabilities. That's where you define how your kernel is going to be, what kernel modules you would like to include. We have a gadget snap. The idea with the gadget snap is to give a personality to a device. You could have the same physical hardware being sold as 3 independent physical devices in the market. And let's say in one instance, you want the USB ports to be accessible to the end consumers. And on the same device, which is sold as product B, you do not wish the consumers to access the USB ports. So by default, you can blacklist certain kernel modules, in this case the USB kernel drivers, from ever loading in the kernel and essentially create a personality for your device and customize it in a way that is seamless for the operation in that product category. And then of course we have on top the base operating system, Ubuntu core itself, which is extremely tiny. And given that it's extremely tiny, anything we need to do that needs to add to the base functionality of the system, such as things that require a uniform access to the entire underlying hardware, such as network manager or a BlueZ5 stack to do Bluetooth or LTE or phono, or anything for that matter. We add that in terms of a framework snap. And then finally on top, we have the applications itself, which could either utilize a framework to offer whatever they wish to offer, or offer a snap which just depends on the base system and does not need any other additional functionality to offer its useful. So in this design, as you can see, everything is completely isolated and kept separate and allows us to do automatic updates for any part of the system without affecting the rest of the system. And if for any reason that update fails, the system can automatically roll back to the previous known working state of the system, essentially giving you a way to field service a device, right? Giving you a mission-critical way to make sure that your devices are not broken in the field. So the whole idea of sandboxing each application is residing in its own space. The idea is very similar to containers that exist today, such as Docker or LXC or LXD. We are utilizing the same kernel primitives, but making it slightly looser for the applications that reside on the same system to interact with each other. For example, 2 applications could send messages to each other over dbus in the Snappy environment, versus in the Docker or LXC environment, they have to pass messages over the network socket and have to incur the cost of encoding on the network socket on one side and decoding on the other side before packets can be consumed between applications on the same physical machine. We have developed a new tool that I mentioned earlier called Snapcraft, which essentially allows you to develop applications in this new environment. You can build from a variety of sources. You can point to your own source. You can point to a source on GitHub, on Launchpad, or anywhere else in the internet. Essentially, build them individually as parts, combine them together using plugins, and essentially be able to create a snap that can then be consumed in the Snappy environment. So we already have ROS core snaps available, and it's an easy way to consume ROS core to build anything on top in the Snappy model and deliver an application that is easily consumable. And we are trying to make our build infrastructure extremely seamless so you can interact with the same way as you do today with Catkin in ROS and consume your physical hardware. Really. So to interact with this new set of devices, we wanted to provide a capability to be able to manage these devices remotely. Right? Once the device is sold, a robot could be not physically accessible. We don't have a console port to the robot or the drone at all times, but we still want to update packages on it. We still want to add additional functionality to it. We built a new web device manager framework, which essentially allows you to remotely manage any device that is running Snappy. You go to the IP address of the device, :4200, where you can access every application that is running on that device. So in this case, you can see some of the sample applications that are available on my Snappy device at the moment. And of course, at the same time, it allows you to access the store and see other third-party applications that are available to be consumed for the architecture we are developing on, and essentially creates a marketplace where people can now sell and buy applications for the physical hardware at any time. So in terms of ROS support in Ubuntu, we have a quote here from Brian, who's the CEO for Open Source Robotics Foundation. I'm sure everybody here is familiar with him, so needs no introduction. But really, Ubuntu Core enables our app stores for open robots and really creates a marketplace that people can innovate and compete for. In this model, like I mentioned, we have the SnapGraph tool, which allows us to utilize Catkin, build packages based on ROS Core, and consume the entire ROS Core, wherein SnapGraph will pull in all the dependencies that ROS Core needs for your application and deliver a snap that can then be run and consumed on your device. So in terms of the momentum, we have options available in terms of BeagleBone Black, Raspberry Pi. We are working with a new San Francisco startup trying to make a new FPGA-enabled SoC called Snickerdoodle, which we think is going to be a fantastic platform for developers, especially in the robotic community. We have availability on the Nook. We are working at the moment to enable Samsung Arctic and the Qualcomm Dragon board, and these platforms should be available for consumption very soon for Snappy. At the same time, we have applications available in the store such as ROS to Snap, which allows you to take any ROS application and convert it into a Snap package. We have a YouTube streamer available already. We have a APM Copter application available from Earl Robotics, which have also developed their Earl Brain running on a Raspberry Pi, consuming Snappy, and be able to deliver applications on a moment's notice. So we also have the Mycroft AI open source voice recognition, which we think is a fantastic capability to offer on a robotics or a drone platform. And then finally, of course, on the OEM side, we have the DJI Manifold, which is another NVIDIA Tegra-based computer running standard Ubuntu at the moment, and in the future potentially will be offering Snappy Ubuntu for enabling this new marketplace on the robotics infrastructure. So to summarize, really, what is Snappy Ubuntu for, right? We want to create an environment to be able to update devices and field service devices after they have left the factory, make sure that applications can run on those devices without breaking the devices, and give a mission-critical way to update these devices at any time without having to worry about breaking the device. So in terms of SoC and boards, we have a variety of combinations that are available for consumption. We allow you to differentiate your hardware and allow you to monetize your hardware after the device sale. and of course offer you a way to provide over-the-air updates to any device running Snappy and offer health checks to make sure that the update is good, and if not, you can seamlessly roll back to the previous known good state of that system. And with that, I would like to thank you and take any questions.
Okay. I have a question. So if we were going to deploy something in an industrial space, do you have a timeline for when you suggest we do that? It seems like most of the apps are targeted for the commercial space where the requirements are less rigorous.
Right. So that's a great question. So for the people on the remote listening audience, the question was, at what time should we start investigating significantly on the Snappy front? Because at the moment, it seems like all the applications available on the store are more for commercial devices, which don't have as stringent requirements as in the industrial space. So I would suggest that 16.04, which is coming out in April of 2016, will be our first stable release and an excellent starting point to investigate on using Snappy as a potential option for the ROS-Industrial. And in the meantime, we have a few robotic companies already utilizing Snappy to build their products and moving forward. So this would be a great time to begin investigation. Any work that is done right now will be easily able to move forward to 16.04. And 16.04 will be our first stable release, allowing you to consume Snappy anywhere you like. Thank you.
Thank you, Manik. All right, next up is Kent Massey. I do want to say that the value in what Canonical is putting out can't really be understated. There's a lot of people who think a robot app store is a really great idea. Well, it was a great idea, but it didn't have kind of the core support you need at an OS level. So now that exists, and I think this is going to be very important to the ROS-Industrial community. And let me bring up Kent's slides. So Kent is from HDT, and he's going to show you all the robots that they have and all the ways in which they use ROS. Kent?
Thank you. Kent Massey, HDT. I just have to figure out which click. There we go. Yes, no? Okay. We sort of built an insane arm and have been figuring out, how to apply it. We started off with the DARPA project. We're trying to replicate a human arm in order to create a prosthetic arm. And you can see from the specs, we actually did a pretty amazing job in terms of its speed, its lift capability, its degrees of freedom. It's also a $500,000 arm. But core to its functionality, built into every single actuator, is active force sensing, true force sensing, using strain gauges, not motor currents. Also, absolute position. So that core technology we then turn into a more industrial, more ruggedized, cheaper arm. Small arms, still has some pretty insane power. You're looking at an arm that weighs less than 2 kilograms that can pick up over 10 kilograms, 120 degrees a second. Dual arms, you want degrees of freedom? I mean, just controlling that is an interesting challenge. Highly dexterous, so anthropomorphic end effectors, which gives you the ability to use human sort of tools rather than special end effectors. And it's very modular. And that kind of gets to the core of the issue that every single actuator, and they go from about 8 Newton meters all the way up to 240 Newton meters. These are self-contained sealed units. Like I said, there's a member in there that we put strain gauges on that experiences a little bit of deflection, and that gives us the ability to actually measure true force and measure it quite accurately. Around that, we measure the absolute position. So, in all of the electronics, everything that needs to happen, you basically put CAN bus and power into this thing, and it takes care of whatever it's supposed to do. You can also pump gigabit Ethernet through it. The internal control loop runs at 500 hertz, and it'll control position, speed, or force. And external communications happen at 50 hertz. So what this means is you can run compliance, and you can set the compliance parameters like stiffness, and you can set these parameters at up to 50 hertz and let the robot, let the arm take care of it. It'll report back to you what loads every single joint is experiencing and what its position is at that 50 hertz. But it will actively deflect, so the arm, if it bumps into something, will actively deflect away using this internal control loop running at 500 hertz. Well, that's great, but ROS doesn't do force control, right? So what does it have to do with ROS? Well, you can. And so here's a little quick example of how. Opening up a door. We all know how robots open up a door. They spend God knows how long with high-resolution cameras staring at the scene, figuring out the axis of the door, figuring out the path, doing all of that good work, and still screw it up. Because it's really hard. But you could teach a robot to open a door like a person. So this is for the people who want to look at the talk later, the definitions of all the different kinds of motion. Basically, all you have to do is get a rough alignment so that the end effector, as it moves forward, is going to wind up impacting the door somewhere above the door handle. You drive it into the door. Bam! But you've made the fingers gushy because you can control compliance. So no damage happens to either the door or the fingers. And at 50 hertz, you get to read the loads building up on the fingers and their deflection of position from position commanded to position actual. And you go, oh, there's the door. I've hit it. I don't need binocular vision. I don't need all kinds of awesome depth perception. I have now discovered the door. And I can bring the hand down. And again, setting some of the wrist actuators to be a little bit softer and firming up the fingers. I know when the end effector contacts the door lever because I experience a twist on the end effector as it's pushing downwards. And so that tells me, oh, I now have got the lever. So I can execute a grasp with nice firm fingers at this point on the door handle. And I can soften up pretty much everything because now, gosh, this is where things get really hard, right? You've got this rotation out in 3D space, and to try to figure all that out with eigenvectors and all you could go crazy trying to, but you don't have to. All you have to do is generally command that rotation of the end effector, and the slop is taken care of by the impedance control, by the ability to make things soft. You just pull the door open. You stiffen up the actuators that are involved in the direct pull motion, and leave everything else pretty loose, and it will sweep the arc for you. You don't have to try to actively control everything. We can open a door in seconds, and have. It's not hard. You just have to do it like a person does it. And we didn't have to teach ROS force control, because all we had to do was set compliance parameters in this event-driven kind of architecture, where we're constantly monitoring the force in the absolute position in each joint and the position error. And because we know the task that we're trying to achieve, we're treating these as little interrupt structures that sort of, divide the task up into the separate pieces and transition our compliance from one state to another. You can even take out gravity. So you know what each module of this system weighs and its pose in a free space, so you can bias the compliance just like you do with a human arm. So I'm holding a human arm out, push it down, push it up, I've got the same compliance in both directions. Or if I pick up a load, I can measure the force that's exerting through the gravity vector and know how much that thing weighs, and again, accommodate for it in my biasing and compliance. So it's pretty cool. You can make something, now, in the practical applications beyond opening doors, material handling, warehouse operations, it goes on and on in terms of why this is a good idea. Okay. Just for funsies, some of the other robots we make that have ROS. I just got back from 2 weeks of jungle testing with this 500 kilogram robot we built for the military to carry gear. There it is, carrying about 500 kilograms of gear out in the desert. That was testing done several months ago. Here's ROS going to the dark side, weaponized robots. So don't go to the dark side. Instead, learn how to control the force, right? I'm sorry, it's Star Wars week. So that's me. Thank you. Any questions?
Somebody up here has. Don't see any, but I have a question. Can you give examples of other operations you've done with force control in addition to opening doors? We've done.
Sure. So one of the things we're working on right now is a warehouse application. So what other examples do I have of force control? Again, so force is really great when you can't count on millimeter level accuracy in terms of where things are positioned. So typical industrial robot has this wonderful sub-millimeter accuracy, but it's counting on the thing it's picking up being located that precisely. Out in the real world, in an unstructured environment, they're not, and it's insanely wasteful to try to locate things that precisely. So if we're going to pick up a tote off of a warehouse shelf, we just have to know kind of where it is. And we can reach out, just like that door example, until we physically contact the tote. And we can then execute the grasp. And as we go to lift the tote, we may not know how heavy it is or what's inside of it. We don't have to worry about it because we'll continue to provide feed-in lifting force until we actually detect the motion. So we're using, in essence, force sensing all through that process. You can get much more fine-grained in terms of trying to align parts and trying to use force sensing there. Again, trying to do some blind alignments. When you get like positioning a shaft on a sleeve, that can be extremely difficult. But if you allow a little bit of force control, you can turn into something quite easy. So those are the sorts of applications that we've played with.
Okay.
Yes, there's a question. I have to get my glasses off.
They're asking, do you have a video of the door opening?
Oh, we do. I wasn't sure about how I was going to be able to present. I just came from 2 weeks of jungle testing, so I didn't know how to get video on here. But yes, there's lots of video of opening doors.
Okay.
And
for HDT?
I don't know that we have any up online. I can send you some and you can put it out or whatever. But it's nothing spectacular. It just kind of looks like a clumsy person opening a door.
It just works.
Yeah. I mean, the miracle is if you step back from trying to control everything by absolute position and use force, you can really treat the world like all of us do as humans. And some things get a lot easier. Yeah.
Cool. Thank you, Kent. So I asked Kent to come talk because he's got really cool robots that do, just a ton of different robots that all use ROS, which is great. Force control is something that industry is really in need of. There's some new platforms that kind of support it, but in an industrial sense, we just don't know how to use it. So I'm hoping that, through talks like this and interactions with, people from HDT like Kent, we can get a better understanding of force control. And Kent, I'd encourage you to let your engineers, push stuff back into the ROS ecosystem related to force control. Even if it's just knowledge and not code, that's still very valuable. So.
Okay.
All right. Next up is Matt Curfman from Intel. And he has a camera that I think we're all going to be very interested in. And we're doing great on time. Everybody, awesome. Oops. There we go.
Cool. Thanks, Shaun. Thanks, guys. It's great to be here. My name is Matt Curfman. I'm a software engineer with the newly formed Robotics Solutions team. This is a team that's a part of the Internet of Things group at Intel. And what we've sort of discovered as we go through and look at the technology that the company has invested heavily in sort of the PC space, a lot of work to enable the capabilities for adding human-like senses to tablets and laptops. And we're like, these would be really compelling things that we would like to build into for our robotics customers. And so we're working with these business groups to drive technologies for robots. We're working to make sure that this is packaged in a way that's easily used by the robotics community. So a large part of that, as we've looked through, is to provide this as contributions to the ROS community. And it's our goal to make sure that our customers can be really great robotics products with these capabilities. There's a whole bunch of things in terms of speech and depth vision and robotic location using Wi-Fi standards. But for the talk today, I wanted to concentrate primarily on the Intel RealSense technology for the 3D cameras. So in August, our CEO made an announcement at the Intel Developer Forum in San Jose that Intel would begin supporting officially ROS for the technology that we're building for these human senses. And the reasons why, I think, have been well documented in the press. Our goal as a company is to ensure that the technology we're providing is applicable and available for any computing device, whether that is a robot or a kiosk or a device at the end of a gateway and an internet, in an industrial setting, or a PC or a laptop or a tablet. And so our team that have been developing the RealSense technology has predominantly been focused on Windows over the last couple of years. And so with this request from the community and with our approval of our CEO, we're very excited to share some of the things we've been doing in this area. My peer, Amit Moran, presented a discussion at ROS-Con in Germany, where we talked a lot about the camera, and I'll do some additional sort of follow-up to some things we've done in that area. So I want to talk a little bit about RealSense for anyone on the call who might not be familiar with it. RealSense is the brand Intel uses for adding those human senses to computing devices. One example of this has been initially in the development of our PCs and laptops and all-in-ones, enabling sort of the computer from a short range interact with the person sitting in front of that, whether that be the ability to recognize the person and unlock their device, or to read their emotion, or being able to use their gestures to control the computer. At the Intel Developer Forum, one of the examples they had on stage was the chef who was going to build a cook in the kitchen, didn't want to sort of touch with his computer. He had messy chicken hands, right, those chicken fingers. And so the ability just to interact with my screen or tablet using gestures is a rich way to sort of break the mold from the keyboard or the mouse. We've also built sort of world-facing examples of that into tablets. We built a different sensor that allows the tablet or device to interact with its world. So this is pointing away from the computer, the person holding the tablet, and doing things like scanning an object and building a 3D model around that, or an augmented reality application by using the tablet sort of as a portal and looking through the real world and being able to interact with certain elements of that in sort of an interactive 3D space. We've expanded that also in the work with the tablets and PCs to have person-to-person interaction, whether that being enhanced depth photography that allows me to take photos of another person and then sort of after the fact make very rich edits, taking advantage of some of the metadata or the depth data that's associated with that in partnership with Google, or even like 3D avatars, or you can combine a lot of these things with gestures, augmented reality. Now, if I have these in both endpoints, some very compelling, interesting new multi-user interaction becomes. But the part that I'm most excited about, and what we're here today to discuss, is how we can use some of that technology to enable robots or kiosks or other devices that exist at the end of the Internet of Things. And so I want to talk to you a little bit more about what we're doing specifically to add these human-like sensing and interaction to computing devices that would exist in ROS. For the certain audiences, I would like to show a picture of, what does a general picture of a 3D camera look like? There might be some misconceptions. This is a very simple example of one of my colleagues' hands with our front-facing camera. On the left-hand side, you see the color image of what you might expect to see with any sort of camera. On the right-hand side is one visualization of a depth image. In this particular visualization, the white dots are reflecting points on the hand that are closest to the sensor. And the darkest dots represent positions that are farthest from the sensor. And we built different sensors for different use cases, and so this would be a good example of that, of a near-field use of a 3D camera. Lots of different ways algorithmically to project or view this. In ROS, we might take that depth image and create point clouds or other different visualizations to drive different applications. What I'm showing now are a couple of the cameras that we have available now. And for the folks that are here in the local room, I have some modules in the room. I can hand those around. They're very small, and they enable the placement of these sensors in places that perhaps we hadn't thought or been able to put together. One example with the top one is our front-facing short projection camera, about the thickness of a couple of quarters put together. Our camera on the bottom, the R200 camera, designed again for those viewing the world use cases. And it's even smaller, about the thickness of a quarter and a half. Today, both these devices, given their lineage being developed for the consumer electronics market, are USB 3 powered and allow very efficient access to streaming the video streams out. In Linux, these look like standard video for Linux devices for those that are working in the ROS community. Not an industrial application, but one application we're deploying commercially with our partner, SwRI. SwRI is a company who has deployed and are building a product called Relay. Relay is a hospitality butler. It's really cool. They have through trials in a few hotels that basically allow the front desk staff, if they have guests who have called, maybe they forgot their toothbrush, rather than sending an employee up to the room to bring those complimentary items, they can put the items inside Relay, and Relay then autonomously navigates the standard hallways of the hotel, go up and down the elevators, and deliver the product to the person's door. It's connected to the Wi-Fi, so when they are there at the door, they can signal that the door should be opened, and then the person will go and greet Relay. They can type in the little code that the front desk gave to them, and Relay's top opens, and they can retrieve the item that was sent from them. We really appreciate the work that SwRI has done. They were sort of one of the initial charter members that began building the ROS wrapper around the camera, and we have learned a lot from working with them and continue to support that for the entire ROS ecosystem. So a couple specs just for those who might be interested. I talked about the two camera models that we have today. The rear-facing camera, the R200, has a minimum range tuned for about 0.5 meter to about 3.5 meters. Its technology allows it to be used outside. So outside we've seen that the depth can get almost up to about 5.5 meters with really good accuracy. Depends upon the illumination and the lighting conditions. Our front-facing camera is tuned with a much shorter range. Its minimum range is at 0.2 to about 1.2. Again, it's intended to be used in front of the laptop. It uses structured light technology for implementing its depth. Both these cameras provide multi-megapixel color streams and VGA resolution depth streams. If you're interested more about these cameras, they're available today. I apologize for the tiny font here. For those in the room, it's a little bit of an eye chart. There's a website that you can go to, click.intel.com/RealSense.html, where you can go and buy these cameras for your evaluation today. They're available in quantities as small as 1 for $99 each. Those come with a USB cable and a nice little housing, so you use them externally. It's not just the little module that I showed in the previous slide. We are also intentionally being involved in the ROS community and putting our drivers and software for Ubuntu 14.04 LTS at wiki.ros.org/RealSense. We have a version up there now, binary only right now. We're working to enable and provide the source to be a good member of the open source community. Please continue to go back and look at that website for updates that we'll be making, not just for the camera, for other technologies we'd be adding in addition to that. Would love to get your feedback and collaborate as partners with that. So in summary, Intel spent considerable resources to build the Intel RealSense technology to add that human-like sense for computing devices. We think this would be really important to deploy in robotics, and many of you here have told me that same. And please join our wiki here and we'd love to work with you to get feedback with the cameras that we are making available, and work with you to enable these modules and building some really cool robotics applications. So thank you very much for your time. And so I have a couple questions I see on the chat window. There is no cameras for now. Any news on when they'll be available? Yeah, they've been selling out as fast as we can post them. My understanding is they've been filling those queues up weekly. I'm told Tuesdays are a good day to go check on the website to see if they're available. And a second question on the chat window was, can I say anything about support for other architectures in the drivers? The software provided for the cameras, there's just video for Linux drivers. So
Windows.
We have support of Windows. I think the question was CPU architectures or operating systems. Yeah, there's no x86 isms in the driver itself. It's just a standard video for Linux device that shows up. So, any other questions here? Great. Thank you very much for your time.
Thanks, Matt. Appreciate it.
So, very exciting sensor, and we're very happy that Intel is participating in the ROS community. We think that's very important. And now, next up is Preben Hjørnet. First thing we want to do is play a YouTube video. I'm going to take a risk and say that's it. Hey! Go ahead, Preben.
So, I'm really happy to be able to show this video by a big accomplishment from Southwest Research and the team at Blue Workforce to put together a first release on a driver for this closed kinematics robot. And I can tell you these guys had a lot of fun to deal with the subjects involved here, because it was kind of unfamiliar to us to deal with that kind of kinematics, but they did a great job, and it's flawlessly able to do full motion in the extended workspace of this new kinematic robot. So thanks to the team in Southwest to help us out here. We just got started, and it's a journey that actually started 3 years ago, as we were quite dedicated that the next robot I should try to add to the robot space had to be born as an open robotics device and platform. And one of the things that are really keen to us, that we want to make sure that the accessibility of this robot will be as open as possible. We realized that there was only one real traction generating open platform that we could rely on, especially as we were targeting the industrial space. And for that reason, we are happy that finally we got to this level where we can show the robot in real world. We had it in simulation for nearly 3 years, so we knew it's going to work. But show me the money, or show me the fucking prototype. It's much better than any PowerPoint presentation. So I tried to make it a little short here. I have so much to tell you, and I only got 15 minutes. But basically, the core innovation here is we were driving to lower the cost and the complexity, and also ease up the accessibility of this robot. So, inspired by Google, we said, let's do it tenfold. And if we can hit that spot, we will probably generate some disturbance in the industry. And piling up all the partners and people that supported things I've done in the past, we managed, without selling our soul to venture capital too early, to get together and do this major innovation, where we lowered the cost, the weight, the footprint, and we extended the workspace of these robots. It's probably not fair to a factor of 10, but we actually added some dimensions to what parallel robots could be compliant for. We saw, even though we managed to, and we were very keen on, and will stay keen on having this as an open platform, we divided it into two spaces. One space is the exploration space, like the maker fairs, the education, research space. They've been crying out to get an accessible robot that they could extend and work beyond specifications without having the exhaustive work of trying to make the mechanics work. And being a former Lego Mindstorm creator, together with our board member, Karl-Erik Skjoldrup, we committed ourselves and said, let's make a robot where you don't have to put together 1,000 Lego bricks to make a moving device that's really sloppy. And basically, this was our idea. Robots of this kind had to be modular and had to be able to be easily modified for different kind of applications. But as we wanted to get in fast and get people to be able to play with this, we defined the Explorer model that you see on the left side, and this is where we made the driver accessible now. It's on GitHub. And the next thing's going to happen is that we will have a more certified device, an industrial device coming up later this year, next year. Okay, so without spending too much time on how to segment the performance of robots, especially in the material handling space, here's at least one way to put it that we are being at least used as a guidance is what is the stairway to heaven in material handling robotics. And what it taught me was that the way things has been segmented and divided in devices more historically than anything that makes sense to the big engineer. So you see here on the right side, this is how the big engineer changed kinematics when the circumstances changed it. It took a couple of million years to adapt to changing environments. And what we tried to is to learn from this guy and say, now we have so much computer power, thanks to Intel and other guys, now we can do it in milliseconds. And if we could materialize that in a manufacturing concept, we will be able to make robots that people simply will be able to reverse the equation and really focus on the motions, more on the device. So let the motion device and your motion requirements and the dexterity requirements define how you configure this robot. And there are definitely very different spaces where the requirements for the robots divides into different clouds. I have 1.4 billion robot cycles to learn from and cloud it in, and it's a story on its own. But basically, you can see here what we have been targeting initially is material handling processes, and that, especially for us, that has interest is the non-rigid, non-uniform space where perception and bionic gripping, and what you were talking about from ATT, the compliance control. For us, it's really important to keep the cost down to a dime, or a little bit more maybe. So accessibility is also about the cost and the compliance. I think ROS is to us the best bridge to make sure it's not a compliance barrier, but it's more a cost barrier. So we will focus on the cost barrier and let the community and share out what we're doing and co-create the compliance and the competence barrier. And we also have been driven, coming out of food, as many of you probably know, we've also been driven in the other end of the food chain of food, meaning the waste. And waste handling is it's a green field for robotics, so there's so much there to catch. But I think the approach has been too complicated, too over-financed, like DARPA projects. It's really hard to carve them down to a viable technology. We try to build it up from the bottom, and together with some Spanish colleagues and so on, we will come up with the first less than $10,000 waste sorting system second quarter of 2016. Probably most of you will say it will be ridiculous to take a parallel robot and do palletizing with it. But at least we've been drilling with some major accounts that's asking us, why wouldn't you do that? If you could scale it up to that space, you don't take up the floor space. Well, it actually seemed like it made a lot of sense. So tray loading and palletizing and packaging is also in our focus. And trailer loading and trailer offloading also have proven to have an insustained state where the need for that is absolutely present. But the current architecture of the solution with the 6-degree freedom of robots and try to maneuver them in and out of trailers is probably not the most viable way. With this robot, where the work envelope and the footprint that it occupies is a 1-to-1 and not a 20% like you are used to for Delta and Quattro robots, it's actually possible to make this robot fit into a trailer. So, it's all new to most of us, even to us. We learn every day. We get new ideas, simply because we also learn to adapt to this world. So 3D printing and this kind of additive manufacturing and open CNC. So the Fab Labs, we have a partnership with the Fab Labs, and we really want to encourage that kind of micro-manufacturing and getting these maker spaces and Fab Labs out of the let's make a party, we did something in a model, but actually make it relevant for manufacturing. So we're trying together with these guys and also to drive them towards ROS that micromanufacturing could probably be with another value chain and access chain be sourced via these fab labs. So we're talking about a new brand called FabFab, that you can go there with your manufacturing needs and you can leave it, and it's only in a radius of 100 miles that you have access to this. So anyway, if you think this is growing over our head, yes, if you look at the right picture, Ragnar is actually growing over my head. So I cannot really follow up on the ideas that people are coming up with. What could be viable for this? And I think with the ROS driver we now have available, it is definitely interesting for us now to look forward and invite people to come up and challenge this and co-create with us. So what we want to do is, now we release this driver, and it will be in open source, it will stay in open source. We will add more capability to it. We looked at MoveIt. There is some challenges where we need to add some more dynamics into MoveIt. So we talked to the guys both at Fraunhofer and Southwest. So we will have projects coming up for the next. Hopefully we can fit it in or add more resources. So this important project, at least to us, we want to ask the community also whether this is an important subject for them to get more coordinated gripper motions within the path to get more dynamics and more throughput out of it. We will add conveyor tracking to this, so you can have non-deductive or motions where this MoveIt program is more to pre-planned paths. I think this is an important subject that is already on the agenda, and we just want to emphasize, even to us, it's very important. We made the first drivers to a fixed model of the Ragnar robot. It's a small deal for us to, from a control point of view, to have it as a parametric model, meaning you can change the arm length and the topology of the robot. It's all about getting the GUI elements to work with us. I think within the next stage, so probably in February, we should have that made available. So I just want to thank the ROS community to really show your commitment to this ROS-born robot. It's not a robot that adopts to ROS. It's born from the idea firsthand. And we're so grateful to come to this stage where we can actually afford and allow people to access it via ROS driver.
Preben?
You're welcome.
Let's see, are there any questions?
Yeah, 5 tons.
Right there. Can you say something about support for other? Oh no, that was for the
industrial version is really up to 5 tons. Yeah, that's actually an application. Yeah. So this will be driven by industrial motors, but these materials that we use easily adds up to 5 tons payload. We have a large-scale industrial project going on where we're going to handle a 5-ton workpiece. Yeah.
I have 2 questions. One is, what is the smallest work volume and what's the largest work volume?
The smallest work volume we do now that will make kind of sense with the modular size will be kind of a Euro pallet size, like a square meter.
Okay.
Yeah, or cubic meter. There are scheduling that we will bring that down. We will make another version where we will squeeze it down to 1/4 of that, meaning it will be a kind of a tabletop robot.
Yep.
Yeah.
And I know we got a prototype to play with.
Yep.
Do you have a timeline for when these might roll out where others can use them?
Yep. Thank you. The timeline was based on we locked down some heavy investments on molding equipment, and molding and the assembly of these devices will start out in the beginning of January. So we can ship products in quantities from the beginning of February. But I think already now we can see that our scalability will be that we can bring quantities from February.
Great.
Yeah.
Well, thank you, Preben.
You're
Appreciate
welcome.
it. All right. Yeah, I think, not only is this robot just interesting from a kinematics point of view, if that's what interests you, but certainly we're happy that Preben has adopted ROS early on and been an active supporter. So next up is Mirko from Fraunhofer IPA. Mirko, can you unmute yourself? Mirko is the only presenter who's remote at this point.
Yeah, I just unmuted myself. Do you hear me, guys?
I can hear you.
Okay, so I do apologize in advance if there will be some outages, but apparently the bandwidth test was not that great. But I heard you loud and smoothly so far, so hopefully should work the other way around as well. So, okay, so is everybody able to hear me? Can I go ahead?
Yep, we can hear you and we can see your first slide.
Okay, perfect. So, first of all, thanks to everybody who is attending this meeting, both physically and online. So, good morning, good afternoon, good evening, depending on where you're located. And thank you, Shaun, for asking me to give the final remarks at this meeting. So, I've been working at Fraunhofer IPA since April, and I've been honored to manage the ROS-Industrial Consortium Europe since a bit over 8 months now. So, I would like to share with you some thoughts. I would like to call them lessons learned from bootstrapping, in a sense, ROS-Industrial Consortium Europe, since we started last year, 2014. So 1 year after the ROS-Industrial Consortium Americas launched, and we broke 10 members. So we are over 10 members now, looking to get close to 15 by early next year. So yeah, let's see what I learned throughout this adventure. So here are my contact details, but always head to rosindustrial.org in case you have questions. And looking back, again, during those 8 months, I've been looking at how the guys did this great job of bringing this concept from again, a concept. So back in 2011, Shaun had this let's call it experimental implementation of ROS on an industrial platform, which was basically the PR2 pick and place application performed on industrial hardware. And again, it was 2011 proof of concept. So apparently it was interesting enough for a number of partners. I saw this video in 2012, actually. I was an industry attendee at the inaugural ROS-Industrial event in Europe. And I think the reactions were pretty good in the audience. So the concept went ahead. And now at 2015, so it's not just a concept. So here are some examples of industrial applications that are either already out in production, like the one in the top left, as you can see, is an AGV system by Bear Automation, made with in collaboration with Fraunhofer IPA here in Germany. So it works 16 hours per day in an automotive plant. And as I can tell you, the automotive industry is pretty stringent on requirements for what concerns reliability. And so quality still is a primary concern to them, but still ROS is able to meet this quality thresholds. You also stuff that you can find online if you just Google for it. So you have agricultural robots, great example, Bosch Field Robotics, based here in Stuttgart. Then you have waste sorting by means of robot arms, top right corner. You have the great examples that we see from Rethink, from Baxter, from here, Sawyer here. And again, now it's 4 years after that. So not all this stuff runs on ROS-Industrial, but for sure the industrial part of it helped to bring this concept of ROS into what we call industrial environments. So again, are we talking about industrial use? So once in a while, I started in June when I was preparing my talk for the ROS-Industrial conference here. I like to go to LinkedIn and try to do a LinkedIn search for ROS robot, and you find a bit of different industries here and there. And from time to time, you also see something a bit unusual, like oil and gas, or stuff that you wouldn't associate immediately with the ROS. And something that I found last week when I was preparing the slides for this talk is a technology consulting firm here in Germany hiring ROS developers. And this is, I think, a really significant indicator that this tool is gaining acceptance, as typically these kind of companies try to recruit engineers for what their customers have a really pressing need for, and they cannot find the market themselves. So again, this is also another indicator that the tool is not, as Shaun said in the introductory slides, it's not a matter of if, but as if how and how fast. So it's happening. So again, reflecting upon this, I also apologize, but I always forget that when we present remotely, you have no transition within the slides. Again, unfortunately, this doesn't come out as nicely, but if we first focus on the left-hand side, so ROS by itself has a lot of merits. So it showed continuous technical progress. The 8 years montage video is a good testimony to that. And I would also say that, this is the new tool of the trade for roboticists. So as students and interns who use it graduate from their studies and move on to industry position, they bring the tool with them. So if given the chance to use the tool that they find most suitable for the task, they for sure use ROS. And if they start a new company, the new breeds of startups are all in for ROS. So you might have read the article on IEEE Spectrum that was out, I think, was it last week or very recently anyway, in which Brian Gerke was reporting this figure, which is just a lower bound of $150 million of venture capital in 2015 alone going to ROS-based startups. So again, pretty significant. And again, talking about Brian Gerke, the Open Source Robotics Foundation does a great job in steering development while keeping it open to external contributions. This is something that really is key to growth, like being at the helm of the development, but keeping it open to what people are putting it to use for around the world. Then ROS-Industrial itself has a lot of merits as well, I believe, since it makes this technology usable on industrial hardware. So as soon as you see ROS running one of those industrial arms, you can probably assume that ROS-Industrial there has some merits as well. It also has some indirect merits, I would say, as in, with our outreach activities, we do make industry users aware of this technology. So it happens to me, especially here in Germany, where a lot of industrial companies, both in the industrial automation space or users, so manufacturing companies that are deeply rooted in conventional manufacturing technology. So when I go to those technology events and I speak to them, and it's like, okay, so interesting, like that's a great tool that I was not aware of. And okay, so maybe I'm not buying the idea today, right now, but I'm definitely looking into that. So this is also, I would say, a merit of the initiative. Providing training is maybe sometimes a bit underestimated, but again, for established industries with technical staff trained in the traditional tools, now having a smooth entry into this technology is also necessary. And also would say catalyzing the developer's interest towards applications and use cases which would have a smaller use base, so they might not be appealing to the vast majority of ROS users, but that are of industrial relevance. So this could be the implementation of some industry-specific technology, communication protocol, again, a driver for some specific hardware. So, Shaun, you can still hear me because I don't have any feedback, so I hope that the line is still on, up and running.
There you
Okay, great. So, again, how did that happen? So we said the merits of ROS, the merits of ROS-Industrial, and I would also say the merits going down specifically to the members of the ROS-Industrial community, which we have a good number of people attending both physically and online here today, which I'd like to thank, and of the two ROS-Industrial consortia. So again, although we have two consortia, which, as you know, have a paid-for membership scheme because there is some management and some focused development to be paid for at the end of the month, but it's still healthy and in the interest of the initiative to have a free and open community and open for the general audience to join, because this is the fresh blood which is bringing new ideas and that we really still keep alive and have a very good collaboration with. And still also having committed organizations who provide the voice of business. So they do provide with user requirements. They do provide us with interesting suggestions, interesting directions in which to look into, at least, if not steer the whole ROS-Industrial initiative is also healthy and important. And they also provide very importantly the financial backing for all the management and the exploratory technical development, which we need to perform in order to keep the project relevant to industrial uses. So bootstrapping ROS-Industrial Consortium Europe, I would say that the primary driver comes from the unfulfilled needs from new application areas. So at least our experience here in Europe is that system integrators and startups who are actors which are very close to new application areas, either because a customer, which could be a traditional manufacturing industry, has a new use case and calls in a system integrator, as it would typically do for its automation tasks to solve the task, or a startup which is venturing into a new application area with a new product. So they come across, again, unfulfilled needs, and they see ROS as a great tool to solve those needs. And we had much greater success with system integrators and startups, other than maybe established hardware manufacturers who already have a good business up and running and might be less prone at first to look at these technologies. A second lesson that I learned is that open source is okay. I remember at the event here in Stuttgart back in 2012, there were many concerns about open source, which seemed odd at the time, since Linux has been doing great in the IT space and also in mission critical applications for quite some time now. So I would have thought back then that the fact that a piece of software is open source does not necessarily mean that it was made by a graduate student that as soon as it was done with the master's thesis would have dropped the thing. And not open source is much more than that, as we all know. So this is now something that I see as something which gained much more acceptance. But still, let's say that reliability is definitely a must. As in, if it's okay for people in the research community to reboot their robot every day as they go home, and the day after come back to the lab and restart with their experiment. In industries where robots run 24/7 for days, weeks, months in a row, and when, for instance, in the automotive industry, you can have a downtime costing you 20,000-30,000 euros or dollars per minute, then reliability is probably the first priority. So give me something that works reliably. It might not be that fancy, but first it works reliably. So any new technology that is bringing in more efficiency has to step up reliability as well. So they're not willing to take a hit there for something fancier. Again, this is something that we are looking at, of course. And I do believe that we can learn something from Linux, for instance, which has been doing something similar, as in graduating from a hobby project to something running mission critical applications way before ROS did. I would also say that's more like both a wish for the future and also an intention as the ROS-Industrial Consortium Europe manager. And I would say that since the project graduated from what was an exploratory effort, you've seen in 2011, the meritorious effort of Shaun in trying the proof of concept. So now it's something that is of clear use and value. So original equipment manufacturers will be expected to back ROS support. So I've seen great things so far in this community meeting, like companies like Intel providing drivers for their hardware. This is great. Like providing ROS support and ROS technical backing is something that we are more and more expecting from OEMs. Also, contribution to the consortium is appreciated as well. So let's think something along the lines of ROS-Industrial officially supported hardware in the future. Again, next year will bring a lot of news under that front. Sorry, here I was supposed to pop up once at a time, but let's focus again first on the left-hand side. So we have, again, fulfill needs, reliability, which is a must, and OEMs are expected to back ROS support. So again, if we elaborate a bit more on those topics, so I would say that industrial users are less and less picky about how you're performing the task if you're able to accomplish the new tasks that the new application areas are presenting you. Again, the stability of the operations definitely wins 100% over unreliable, no matter how fancy solutions. And again, it is time and money expensive to support the increasing selection of ROS-compatible hardware that the ROS and ROS-Industrial support. And since ROS-Industrial can be shown, maybe not with hard figures so far, but can definitely be shown to a certain extent to generate hardware sales, we would expect companies to chip in, so to speak. For us consortium managers, but for the community at large, I would say that for the future, some suggested action items is that if we want to further push ROS adoption, a good driver is to develop ROS solutions which target needs not addressed by current technology. And again, we've seen today some very interesting stuff. I really like the force sensing example from HTT. On the reliability front, let's keep focusing on documentation and testing. And there was a great addition recently that we talked about in a developers meeting, the support for Travis continuous integration. And you users out there, like you're part of the community and you're probably a user as well, I would say put pressure on the manufacturer of the hardware that you're using and that you purchase. Put pressure for them to provide us assistance, technical assistance, or at least financial backing to the consortium for us to provide assistance. And with that, I would like to thank the community present here and also those who were not able to make it to the meeting and our great members for their continued support. So thank you. I'll be happy to take questions.
Mirko, can you see the questions on the left-hand side there in the chat?
Yeah, so I have a few questions from Walter. So he asks, so what is the comparison in downtimes between code developed from scratch at a company and what is in the open source world? So that's a great question, but unfortunately, this is the kind of questions that I'm looking hard to find hard figures to back what our intuitive idea is, which would be that at a company, especially a small one, like I was a developer at an industrial automation company myself, and even though company executives would like to think that their technical staff is the best in the world, you're typically overworked and bound to deadlines. So it's not necessarily that this proprietary software is much better than open source software in terms of reliability and therefore downtime. So there is no single hard figure. I would say that a good indicator is that a piece of code. So some of the ROS libraries, for instance, that we use that are deployed, in numbers around, are for sure exploring the test space much more than some proprietary code that runs in a single plant. So again, no hard figure, but I would say that intuitively, the open source world at least test the the test space much more. And then the other question is, so I see open source software take advantage of unit testing and automated testing more than I have seen a commercial company. I totally agree. Yeah. I would also say that the fact that the code is on GitHub makes developers a bit more, they put pride in what they do, and so having code which is better documented and with unit tests is sort of encouraged by default as soon as the software is open. So I do agree, and I see those features more on open source than I've seen myself in code software. And for what concerns the Travis continuous integration, well, I would say that very good reasons that it's free for open software and easy to set up. But I would suggest you maybe, Shaun, to chip in on this answer. So I would say that it was just easier to set up. But if you have any other reasons, feel free to elaborate.
Yeah, Mirko, and thanks for your talk. Travis was easier to set up. We actually use both still, so we're not picking one or the other. But Travis allows us to evaluate pull requests, which is very important in open source projects. So thank you, Mirko. Thank you, everybody, for coming today. Thank you to the presenters. Thank you guys that all showed up in person. I appreciate that. It could have been me in a big lonely room. So I got some upcoming events up here. Feel free to read through them. Yep. So That's it. That concludes this ROS-Industrial meeting. We will have perhaps the important event is the next community meeting, which will be, again, public and online, this time at a much more European-friendly time. My apologies. I'm learning as I go. In February, and we'll have it at 9 a.m. U.S. Pacific time, which means people in Europe won't feel left out. I apologize for that. But thank you.
Thanks, everybody.